Niels Bohr, a revolutionary physicist. Born in Copenhagen, Denmark in 1885, Bohr became a giant in atomic theory. His work revolutionized our understanding of the atom and laid the foundation for quantum mechanics. Bohr's contributions earned him the Nobel Prize in Physics in 1922. Bohr's fascination with the atom began early, inspired by Ernest Rutherford's model. However, Rutherford's model couldn't explain why atoms emitted light at specific wavelengths. Bohr set out to solve this puzzle, and his groundbreaking model changed physics. He established the Institute for Theoretical Physics in Copenhagen, attracting the world's leading physicists. At the Institute, Bohr fostered an environment of intellectual ferment and collaboration. His legacy continues to inspire scientists today. In 1913, Niels Bohr introduced his revolutionary model of the atom, which would forever change our understanding of atomic structure. Bohr proposed that electrons orbit the nucleus at specific energy levels, much like planets orbit the sun, a concept that was both innovative and intuitive. These energy levels were quantized, meaning electrons could only exist at these discrete levels, and not in between them. When an electron transitioned between these levels, it emitted or absorbed a photon of light, a process that could be observed and measured. This concept explained the spectral lines observed in atomic spectra, which had puzzled scientists for years. The Bohr model provided a simple yet elegant explanation for atomic behavior, making complex ideas accessible. It was a powerful tool for introducing students to atomic structure, and it remains a fundamental part of science education today. However, the model had limitations, especially for atoms with multiple electrons, where it couldn't accurately predict behaviors. Despite its limitations, the Bohr model represented a major leap forward in understanding the atom, influencing future research. It paved the way for more sophisticated quantum mechanical models, which continue to build on Bohr's groundbreaking work. One of the Bohr model's greatest triumphs was its ability to explain spectral lines, which had puzzled scientists for years. Classical physics failed to explain these unique lines observed when light from excited atoms passed through a prism, leaving a gap in our understanding. Bohr's model offered a clear and revolutionary explanation. Electrons absorb energy, jump to higher energy levels, and then release energy as light when they return to lower levels. The energy of the emitted light corresponded precisely to the energy difference between these levels, making the process predictable. Since energy levels were quantized, the emitted light was also quantized, meaning it could only take on specific values. This meant that atoms could only emit light at specific wavelengths, which appeared as distinct lines in the spectrum, a phenomenon that was now clearly understood. The Bohr model's ability to predict these spectral lines provided strong and compelling evidence for the concept of quantized energy levels within atoms. This groundbreaking model revolutionized our understanding of atomic interactions with light, paving the way for modern quantum mechanics. Section 4. Limitations and the rise of quantum mechanics. The Bohr model was a groundbreaking development in atomic theory, but it had significant limitations. It couldn't accurately predict the spectral lines of more complex atoms, and assumed that electrons orbited the nucleus in fixed, circular paths. Quantum mechanics later revealed that electrons exhibit wave-particle duality, meaning they can behave both as particles and waves, and don't have fixed orbits. Heisenberg's uncertainty principle further demonstrated that the precise position and momentum of an electron cannot be known simultaneously, adding to the complexity. The Bohr model also struggled to explain the Zeeman effect, which is the splitting of spectral lines in the presence of a magnetic field. These limitations highlighted the need for a more comprehensive and accurate model of atomic structure. Quantum mechanics, with its probabilistic approach and advanced mathematical framework, emerged as a more complete and accurate theory. Despite its limitations, the Bohr model introduced the concept of quantized energy levels, which became a cornerstone of modern quantum theory and paved the way for future discoveries. Section 5. Bohr's enduring legacy, shaping science and thought. Niels Bohr's contributions extended beyond his atomic model. His Institute for Theoretical Physics in Copenhagen became a global center for quantum mechanics research. Bohr mentored physicists like Werner Heisenberg and Wolfgang Pauli, who made significant contributions to quantum mechanics. His emphasis on observation and interpretation sparked intense debate and shaped the philosophical landscape of the field. Bohr's model remains a valuable tool for introducing students to atomic structure. His contributions laid the foundation for countless technological advancements. Bohr's legacy as a brilliant physicist and visionary leader continues to inspire generations.